So the previous slide deck was kind of speaking in terms of generalities. What are the kind of, regardless of what specific hardware you have, what are the things you can expect? In this slide, we're going to go through kind of a survey of what exactly is available at the 3 Office of Science major compute facilities, so you can kind of map those generalities into specific things. And this is going to use a lot of material from several people. So this isn't my data or my figures here. So it's kind of taking a cast of people to pull this together. But this slide deck has a lot of information in it. You can maybe refer back to it. You can look on the box folder and see, refer back to this if you want some details. So if we look at what a DOE compute facility looks like in terms of from a data-oriented perspective, the big blue box sort of in the middle is your computing platform. That's going to be a system like Summit or Theta or Cori. But there's a lot of things that go along with that to process your data. When you're moving data from the outside world, the left side, into the compute facility, you're going to usually go through data transfer nodes. These are the things that run Globus and other kind of data access mechanisms so that you can get things in and out of your compute facility, maybe to your local site or to sensors or wherever you're doing. Once you've got through the data transfer nodes, there's going to be a facility or site network. And that is where kind of your big shared resources like archival storage and your center-wide storage are going to be. Archival storage is for long-term. This often tape backup, so things that you want to maintain and be able to refer to for a long time. The center-wide storage, the purpose of that is to be able to share things between users and between systems in the facility. Once you get to the actual compute platform itself, it may have its own platform storage. That's to the far right, which is kind of the high capacity, high performance storage that is for your calculation time, things that you need at runtime in your job. And increasingly, and almost always now, there's also some embedded storage, which is like an even faster tier of storage that you have for short-term use. And it's within the compute system, like it's right there with your compute nodes and has very low latency. It avoids a lot of the hops that I was talking about in one of my earlier slides. So what does this look like as an example? We'll look at Theta. Theta is a Cray XC system, and it does have some embedded storage. It has a SSD on each compute node, just an independent SSD per node, so you can have each set of processes on a given node access data locally with high speed. It has platform storage over to the right. It's called Theta FS0. It's a 10 petabyte file system that was stood up when Theta was turned on. On the facility side, the archival storage at Argonne is a 300 petabyte tape archive. And the center-wide storage is actually 2 file systems. There's Grand and Eagle. One thing that's a little bit unusual you may notice is that Grand and Eagle are actually considerably faster than the platform storage. That wouldn't normally be the case, but the fact of the matter is Grand and Eagle are much newer than the Theta FS0 file system, and so they have more speed available. And there's sort of a shift towards how we're going to be using these storage systems in the future. Now, if you contrast this with Cori, which is another Cray XC system at NERSC, their embedded storage, the big difference, they have archival storage and center-wide storage also. I don't have the specifications there. And they also have a platform storage, Cori Scratch, which is similar to the platform Theta FS0 storage on Theta, but faster. The key difference the thing that's really different between Argonne and Lawrence Berkeley Laboratory is the embedded storage, where Theta had individual flash drives on compute nodes that you could use per node. Cori has what's called a burst buffer. A burst buffer can be shared between compute nodes, but you allocate it with your job. It's a temporary kind of scratch pad that's considerably faster than the platform storage. And you kind of allocate that with your job and you get a dedicated slice of the burst buffer. Then on Summit, Summit is different yet again, It has archival and center-wide storage like the other facilities did. The embedded storage is a little bit more like Theta in that there's no local NVMe drives that you can use for storage. There's something missing from the this diagram though, in that there's no platform storage at all. There's no dedicated file system just for Summit. And the reason is they've made a very large, very high performance center-wide storage system. This is the Alpine file system that has a 250 petabyte capacity. And the reason they've done this is they've invested more in making that file system the best it can be and having it be independent of the compute platform. So as they upgrade systems, the center-wide storage stays the same and is kind of wired up in such a way that it can be high performance for whatever platform they deploy. And this is an eye chart. I'm not going to go through it, but it's here for your reference if you want to look back at these slides later. But this contrasts the three big systems here, Cori, Theta, and Summit, and gives you an idea of what the differences are between them, so you can kind of see what capabilities are there. Now, yeah, none of these systems stay the same forever. We usually expect a given platform to last, I don't know, maybe 5 years. And so we're already talking about what the next systems are going to be. Here's what you can expect at Argonne's exascale system. It's called Aurora. And when Aurora is delivered, it's going to change things yet again. Instead of having a set of independent hard disk drives for each compute node, we instead have a platform storage system called Deos. Deos is going to change things because it's not a conventional file system. It's really an object storage system, but you can layer something that looks like a file system on top of it, so you don't necessarily have to change your application. But Deos is designed to take advantage of NVMe drives and persistent memory to kind of get latency down and get performance up for your platform access. So that's going to take the place of having embedded storage, just kind of blurring the lines between platform storage and embedded storage. The center-wide systems will stay the same. We'll still have the Grand and Eagle file systems. They've been built with Aurora in mind, and we'll still have the same archival storage system. At NERSC, when the Pearl motor system goes live, it's already on the floor, or at least a big chunk of it is, but it's not in production just yet. They're going to maintain their same archival system that they've had, the same center-wide storage that they've had, but they are also changing their platform storage. They're going with a all-flash Lustre volume, scratch volume that's going to have a relatively small capacity compared to scratch volumes they've had before, but with a very high throughput. So this is kind of their take on this, how to do the platform storage and embedded storage. And this is a chart with not just Aurora and Perlmutter, but also the Frontier system at Oak Ridge, where we have details. Some details have not been announced yet. And all of this is subject to change. As you know, these systems aren't live and in production just yet, but this gives you an idea of what capabilities are coming down the pipe. So as these systems are, especially as these new systems are coming online, that means that we have software, DOE software in some cases and vendor software in some cases that has to be updated. This is sort of a summary of some of the things that are available to you and how they are changing. So our IO libraries are all moving forward. They're all being optimized for the new platforms. They're all going to continue to use conventional file systems, but in many cases, these libraries are also being optimized with internal APIs that can support new kind of a little bit more radical storage systems like the Deos system that will be at Argonne. We have checkpoint and restart libraries like SCR, Veloce, and Unify. And they've been working with kind of deep storage hierarchies for a long time. And so it's going to be relatively easy for them to adapt to new combinations of storage hierarchies. It's more of a sort of a policy decision of how to use them best on each platform. There's tools available for kind of understanding your IO. We'll be talking about Darshan here shortly. And Darshan is adjusting to these systems by adding new modules that capture information about kind of new types of storage systems. And that work is ongoing. And then you might also be aware of some of the compression tools that are available. There's two big ones in the DOE, SZ and ZFB. The algorithms themselves are not really changing much with the new platforms. So the focus on the compression tools is kind of making sure they're more accessible as time moves on, so they're not hard to use. So that's kind of a whirlwind tour of the HPC storage systems that are available right now. I just kind of wanted to give that as an example of how the rubber meets the road. But please look back at these slides. You're welcome to reference them. I know that's a lot of kind of facts all at once. So we've got, let's see, just a couple minutes before Shane Snyder does the next presentation. So if you have any questions while we have a minute here, I'm all ears.